I sent you. Alrighty. Alright, hello. How are you doing today, Susan? I hope you're doing really well. Hopefully today is going really good. In good shape today, hello? I'm doing very good. It's been a glorious day already. Already been a very nice and glorious day. How about yours? It says hopefully your weekend was good as well. I hope so. I hope your weekend was good. Ujwal, my friend, how are you? Rihanna, hey! How are you doing? You doing good? Went by fast? Very good. Doing good. Excellent, Ujwal. How was your weekend, man? Good. This year. Holly, how are you? Are you doing well? I hope you guys are doing really well. Good. Sha, hello. How are you doing? How we doing today? Good. Very good. Sorry, guys. Just have to send out an email there. But there we go. And I got your undivided attention. Apologies about that. Apologies. Let me put that there. Bam. Hello, Mazdi. How are you? How are you, my friend? I hope you're doing good. What am I doing today? I don't even know anymore. I'm supposed to be doing something. I'm like, do things. Chillin', working the homework all day. Fair enough, my dude. Fair enough. I believe... No, that's not what we're doing. Alright. Yeah, there we go. There we go. Let's do nerdy things, ladies and gentlemen. Let's do some nerdy things. I like nerdy things. It works. It works well. Alright. I think we're getting close to being ready here. Yes. Alright. I'm doing very good, Brianna. It's been a good day already. Alright. Okay. Let's do this, ladies and gentlemen. It is now 6 o'clock. Oh man. Time flies by when you're doing a lot of stuff. I ain't gonna lie. Alright, but we got work we gotta do. Work. You know, those things that we never want to do but kinda have to do because it's a thing. Yeah, you know what I'm talking about. Things. Things that we don't want to do. Alright. In any case, let's go ahead and get started here. Alright, let's do this. Okay, let's get started today. Welcome back. Welcome back to Monday. Hopefully a nice weekend. So today, we are going to be moving forward here in the book. Last time we finished up chapter 4 and we discussed about the test and we did some examples there from the, so a couple of homework problems and whatnot. Today we're going to need to move forward here, starting with chapter 5. Okay, so chapter 5 is going to be the next chapter in the textbook. All right, so let's go ahead and get going with that here with the first couple of sections of chapter 5. I think what did I put here? Oh, I put the wrong 2 sections there. No wonder I was looking at that. I'm like, oh, I did that in my other class, but not here. That wouldn't be very good if I gave you the wrong sections. Oh boy. Alright, yeah, update the stream info there. There we go. That's a little bit nicer. There we are. So hopefully everybody had a wonderful weekend here today. Got some important things that we have to do. So let's eventually I'm gonna find my way back to sanity. Alright. Spread that way. Alright. Okay. So let's put up let's put up this thing. Let's go to the big board. Let's go ahead and take a look at what we got here. We got the book, but more importantly, we're going to start with section 5.1. So we're going to look at the 5152 handout here, and we're going to talk all about that there. I cannot speak Welsh, Connor, if that is Welsh. I'm guessing that's Welsh. Maybe it's Welsh. Maybe it's Irish. Maybe it's maybe. Welsh is a completely different language. All right. Okay. By the way, before we get started here, sorry. Are there any questions for from the test? At least details regarding the test or whatnot. It's Irish. It says hello. Oh, thanks, Connor. It's Irish. Fair enough. Wait, Irish and Welsh. I know they're 2 very different languages, but I since I haven't heard either, I can't differentiate between the 2. To be fair. Are there any questions anybody has over the exam or exam details? Nope, not yet. Okay. Yeah, don't forget that the exam there is due this Sunday. Okay, so this Sunday is when this exam is due. All right. That also goes along with the homework there. Not gonna think of. Okay. Yeah, just again, all the homework from chapters 1 to 4, and the exam is due Sunday. All right, so be sure to finish it by then. All right, so let's talk about some good things here in chapter 5. All right, so what does chapter 5 entail? Well, chapter 5 specifically entails probability. Probably one of the funnest chapters in this book. Talks about the chances of something happening or certain situations or scenarios happening. And so, what we're going to do is talk about basic probability here today. All right, we'll talk about how to some probability rules, of course, along with the a new rule here along to go along with probability here. One of the things that's going to be very important in this particular chapter is wording is going to be incredibly important. So wording is something that we do see quite often in various word problems. Again, most of this class here is word problems of some scenario. So when we look at wording here, we want to interpret the wording here properly in order to apply the correct probability rules, okay, given that particular situation. Now, before we totally get to that point, and that's going to be a preview there of section 5.2, let's talk about some basics here that we could see in section 5.1. So let's look at question 1 here. Question 1 here says, what is a sample space? Really quick question here. Can you guys actually read that, what I have highlighted, or do you want me to make that bigger? That was one of the things I just want to quickly ask. Can you guys read that or no? Should I zoom in and make it a bit bigger, or make the font size a bit bigger? Yeah, everybody's eyes is different because my eyes are terrible. So I just ask. Yeah, it's good. Okay. All right, I'll leave it alone then if there's no complaints about it. All right, so let's take a look here. What is a sample space? All right, so the sample space has a notation here as the letter S. Okay, so the letter S here represents a sample space. Now, what's the definition of a sample space? A sample space is a collection of all possible outcomes in a probability experiment. So if we flip a coin, for example, then the sample space here will be heads and tails. Okay, those are only two sides to the coin, and those are the only two possibilities that you'll get here for flipping a fair coin here. It'll either land heads or either land tails. Okay, one of those two. Okay, fair enough. Okay, let's go to number 2. Number 2 says, as we'll discuss here quite often in this chapter, is what is an event? All right. So an event is a collection of outcomes from a probability. So again, that form. So basically, this could be oh, it's actually interesting. Um, so a collection of outcomes from a probability basically is an event. So you can assign a letter E or A or B. I will call it usually A or B, like capital A or capital B. It's just a little bit easier to work with. But you can literally call any event. Okay, that's the thing that happens. So as you can see here, the example would be rolling a 4 or rolling a 5 or 6. So we want to find particular probabilities. We say, okay, what's the probability of, say, rolling a 4 on a 6-sided die, for example? Okay, so just as a simple example here, the probability of rolling a 4 on a 6-sided die, what that is, go ahead and compute that out. Or again, the probability of rolling a 5 or a 6. Okay, we'll figure out what that probability is, and we'll see what we get. Okay. All right. Now, another question that will pop up from not just in this chapter here, but other chapters as well, is going to be question number 3. So let's go over that here really quickly. What is an unusual event? So some questions here will pepper in saying, is this unusual or is this not unusual? Now, there is a metric that we do use here. We do use a standard here. And the standard here is that if the probability of that event is going to be less than 5%. So if it's less than 0.05, that's going to be an unusual event. Hey, Natty, how are you doing? We're just underway. Going through some of these quick questions here regarding probability. So if you have your hand out there, Natty, that's where we're at. Question number 3. Okay, so you'll see this quite often here. Not quite often, but you'll see this in several questions here. You'll see, okay, well, what is this? Do you find this probability to be unusual? Maybe that's what it'll say, and you're like, oh, let me take a look at the probability I found and compare it to 0.05. It's less than 0.05 or less than 5%. All right, that's considered unusual, and that's the metric that we're going to go by off of. Okay, I'm doing very good, Natty. Thank you. Okay, so now the question is, what exactly is the notation for a probability model? The notation that we're going to use here specifically is going to be capital P of A, where A is the event of some variety. So I may write, for example, here, I may not write a letter here. Maybe I'll write, for example, here, like P of, say, rolling a 4. Okay, so let's say I roll the probability of rolling a 4. Now I said, okay, here you go. Tell me what the probability of rolling a 4 is, depending on which side of die that you got, and then we can roll with that. Fine. Okay. I know I've went a little bit fast here, but are there any questions so far? Any questions? Nope. All right. Remember, if you have a question, then ask your question there. If you don't have a question, just say no, and I will move on. All right. All right. Can I go back to the top? Yes. There's the top there. All I have up here is just the header. There you go. Let me know when you're ready, Natty, and we'll move on. Okie dokes. Got it. Ooh, no problem. I'm here to help. Okay. All right. Let's take a good look here. We got to talk about some properties of probabilities. Now, this is important here, okay? So, the first thing is that we need to understand is that the probability of any event, the probability of regardless of whatever event that we work with in any circumstance, has to be between 0 and 1, where we include 0 and 1. So, it has to be between 0 and 1 inclusively. All right, so either 0%, 100%. Okay, 0% being it's impossible, 100% means it's a certainty. Okay. If we have multiple events, okay, so let's talk about what comes after that here. It says if the sample space S is equal to a bunch of events, let's say n events or whatever, then the sum of all the outcomes in the sample space must equal 1. So if we took the probability of everything in the sample space, so we took event A1 and event A2 all the way up to event AN, then if we add up all those probabilities, whatever those probabilities are, somehow, some way, they have to equal to 1. All right? If you're solving this, then express it as a fraction. If possible, do the division to reduce confusion. So some cases it may just want you to do fractions. Some cases will just want you to put in a decimal there. All right? Just doing the division out to just put it as a decimal. You're like, fine, you want it as a decimal, okay. some questions are going to be like that. Most of the time, I'm going to be dealing with decimals here. So again, one thing I'll iterate here in this particular case is most of the time in this chapter here, we're going to go out to 4 decimal places. So 4 decimal places is going to be our standard MO here. All right. Okay, so 4 decimal places here will be the usual standard for most of these answers. All right. Obviously, it depends on what my math lab wants for homework or the tests, but typically they'll go out to 4 for most cases. So I'm just preparing you now, so that way you're aware about what the expectations are. Okay. Now let's do a quick example here. All right. So we're gonna showcase this out here a little bit, and then we'll look at some other examples. Okay. Go to y'all. Um, what what has happened here? Why has this happened? Um, all right, perfect, perfecto. Someday I would like to get to a particular spot. Hey, I made it. All right, good job. All right, so let's take a good look here at number 7. All right, so let's look at number 7 here on the book. Okay, we're going to look at the table right here. Okay, so this table that I'm circling right now. All right, this is what we want to look at. So here we have red, green, blue, brown, yellow, and orange. Okay, this is what we have here. All right. So the question becomes is this a probability model? Does this reflect a proper probability table? All right, that's the real question here. So is number 7, so let's look at number 7 here. Is number 7 a proper probability model? Let's go ahead and make a poll here. Let's make a poll. Let's actually do a prediction. You guys can bet channel points on it because reason. All right. All right. So we'll say yes or no. Simple enough. So you can bet some channel points here. We'll go for 2 minutes. Let's do it. So bet your channel points. Your channel points are that thing on the bottom. You don't have to worry. Just they don't mean channel points don't mean anything, but you can make the correct prediction here. Yes or no? Bet your channel points now. Do you believe number 7 is a probability model? Yes or no? Holy smokes, I'm gonna put 3K. Dang. Dang. 3K on yes? Woo. A lot of points. Grant put 2,500 points. Wow. A lot. You guys can predict up above here, right above the chat. Want to bet some points, either yes or no? Like 7 people here. All right. We have 45 seconds to go here. You can bet as many points as you want, but it is what it is. 40 seconds to go. All right. All right, got 10 seconds here. All right. All right, let's put our prediction down here. And our prediction outcome is... the answer is yes. Yes, that is correct. So people who said yes got their channel points back. All right, very good. So the answer is definitely yes. All right, it is a probability model. Let's talk about why this is a probability model first and foremost. First thing is that the probability here, if we take a mine isn't working, but doesn't it have to equal 1? Yes, that is correct, Holly. Two things that would have to satisfy this here. Exactly as you stated there, Holly. If we added up all the probabilities here in this little table, we take 0.3, we take zero point 0.3 plus 0.15 plus 0 plus 0.15 plus 0.2 plus 0.2. If we added those up together, we indeed get 1 here, because everything has to add up to 1 at the end of the day, no matter how silly the probabilities look like. The second thing that we have to satisfy is that all the probabilities here are between 0 and 1. As long as they're between 0 and 0 and 1 are included, then that's the other condition that you can also take into account to know that it's a proper probability model. Hey, Yusuf, my day has been very good. I hope your day has been very good as well. All right, so that's how I know 7 works. Okay, 7 is a definitive probability model at the end of the day. Okay, let's take a look at some more here. All right, I'm going to do some more because reasons. All right, pretty sure that reasons. Good. Today I got some tea here, Yusuf. So all I got is tea. I gotta go and get some new drinks, man. I ran out, and I need to get some more. That's what I need. So new drinks are on the horizon. Unless you guys want me to get my other drink. I have one more drink in the fridge. So, I don't know if you guys want me to get that drink. So I have one more new drink in the fridge. You guys want me to get that drink? I'll leave it up to you guys. You guys can say yes or no in the chat. Um, yes. Okay. Oh no. Okay, fine. I mean, it isn't the grandest thing in the whole wide world, but it's a thing. Okay, we'll get it. This in my drinks direct from the fridge. So I got this. I got this Kimbo Thai tea drink. Okay, so some Thai iced tea type of drink. Yeah. So that's that's my drink right there. The last one there. So the last new one I got here. So I can't go wrong with the Thai tea drink. Okay, I ain't gonna lie. But since you guys asked, then gonna go. This stuff is good. It's pretty sweet though. So it has quite a bit of sugar, but it's good. It goes down so well too. I ain't gonna lie. Um, it's like the mango drink. Absolutely outstanding. All right. It is good. All right. Let's go over a couple of problems here. I'm going to do one of them here, And then I'm going to go ahead and put another one here. So let's look at 16 here. Let's look at 16. How much sugar does it have? It has 34 grams. 34 grams of sugar. 34 grams. But it is made of it's got some creamer in there. It's got direct sugar, some palm oil, some other stuff. Yeah. It's not as crazy as like a Pepsi or a Coke. So that stuff there, holy smokes. Now that stuff's super sugar. Or as everybody knows, the most sugary drink in all of Chicago, as everybody knows, okay, is a Portillo's chocolate cake shake. So, if you want the most sugary drink known in this area, the Portillo's chocolate cake shake is by far the most sugary drink ever constructed. Yes, it is super delicious, but it is super bad for you. I have that drink once a year because I know exactly just how crazy sugarified that drink is. It is ridiculous. Good. I ain't gonna lie. Yes. Absolutely, absolutely true. I gotta look this up now. Now I'm kind of curious about how far this is gonna go. Holy crap! Okay, okay. I'm gonna bring this up on the screen here, and everybody can just go ahead and look for themselves. There are 197 grams of sugar in a large chocolate cake shake. 197 grams of sugar. Holy crap. Holy crap. My goodness. Ooh. I is right. Ooh. Ooh. Just reading that just makes me just, oh man. Oh. Oof. That's a big oof right there. Mercy. Let's see how much a small is. A small is 114. Yeah, the small is just 114. Jeez. Jeez. Yeah, they give you the total carbohydrates of 46%. Yeah, you're right. You're right. You're right, Mazdy. You're right, my dude. It's totally true. It's totally true. Holy smokes. All right. I've seen enough of that. All right. That's like, gee. Oh, just looking at it just makes me like kind of cringe a little bit. Oh, I'm a big dude, but man, I can't even handle that. It's crazy. All right. Let's take a look at an example here. Let's look at number 16 here. Number 16. Suppose you roll a die 100 times and get 680 times. I believe that. I believe that. Contains a lot of mayo. That's a lot of sugar and mayonnaise. I believe that. A lot of sugar and mayonnaise. 100% or more. All right. So let's look at 16 here. 16 says, suppose you roll a die 100 times to get a 680 times. Based on those results, what is the estimated probability that the next roll results in a 6? All right. What's the estimated probability that the next roll results in a 6? So let's assume that this is a loaded die. Okay, so it's a loaded die and a 6 comes up quite often. %. Okay, good. So there's 8 possibilities. So we have 80 over 100, right? If this is a loaded die and it's an unfair die, and a lot of times 6s come up for whatever reason, it's going to be 80 out of 100, which is 0.8. All right, so that's fair. No problem. Let's try another one. Let's try this. This one's my own here. This time, let's assume that we have a fair die, a fair 6-sided die. So let's go with the fair 6-sided die. So let's go with the idea that the probability that we roll a 1. What's the probability that if we roll a 1 on a fair 6-sided die? What is that going to be? Probability of rolling a 1 on a fair 6-sided die. Okay, give me a fraction with that. Man, how'd we get that? 1 out of 6, right? So there you have a number of possibilities here. We have one possibility of getting the 1 out of 6 possible things on the sample space. So there's 6 numbers in the sample space. 1, 2, 3, 4, 5, and 6. Okay? And there's one number, 1, that we can possibly get if we roll a 1. Okay, so 1 out of those 6. Let's try this next one here. What's the probability of rolling a 2 and 4? 2 or 4, sorry. What's the probability of rolling a 2 or a 4? Can anybody tell me what that is? Give me a decimal or you can give me a fraction, whatever. Probably a 2 or a 4. 2 out of 6. Yes, that is correct. Yeah, absolutely right. Okay, so 2 out of 6, 2 numbers on the die out of 6 possibilities. And then again, you can reduce that exactly to 1/3, which is absolutely correct. And then you can figure that out, of course, 33.3% repeating all that jazz. But that's correct. Okay, very good. Go with what's the probability here of rolling a 3 and a 5? Probability of rolling a 3 and 5. Put a little poll here for this one. All right. I put 3 things in here. All right. So probability of rolling a 3 and a 5. So again, 1/3, don't know, or other are your choices. Go ahead and vote now. Got 30 seconds to which to vote here. All right. All right. It's got a few people there. All right. 50-50 here. All right. Yeah, this one's actually pretty close. All right, time's running out. Okay, so some people, so 56% said 5. If for 5 people said other, 4 people said 1/3. Okay, so for the people who put other here, you put 1/12. Okay, where would we get 1/12 from? How would we get that? Kind of curious where you got that from, Mazdi. 0.5 over 6. Not sure where you get the 0.5 from. Like it's like a half times a sixth. So okay. Not quite though. I can kind of see where your logic is going there. Because it says 1/6. So are we assuming that there is 2 rolls? No, actually we're not. Actually, that's a very good question, Grant. We are not assuming that whatsoever. We're assuming 1 roll. Very good question though. The answer here is going to be 0. 0 is correct. And that's a very good question that Grant asked. Yes, that's a very good guess. Because as soon as you think that there are 2 rolls, it's assuming that there's no longer 2 rolls here. There's just the 1 roll, and they have to be both a 3 and 5 simultaneously, which doesn't make any sense on a 6-sided die that only has 1 face showing up. Okay, so we can't have 3 and 5 show up as the same face after rolling a 6-sided die. That doesn't make any sense. Okay, we're not in quantum mechanics here. Okay, so quantum mechanics, you can have 0 and 1 appear at the same time. On the other hand, that doesn't work with the die, unfortunately. All right. Now, I want you to take a look at why I've asked these questions in the way I have. Okay. Ah, very good question here. Okay, very good question. How is 2 and 4 1/3? Okay, now take a look at the wording here. Because it's or, that's right. Because this one says or and this one says and. Correct. The wording here is like I mentioned here. This is just a beginning here of part of chapter 5. The wording here right away is going to throw you for a loop if you're not careful. Okay, that's why I put these particular ones that I have here. I put them in because it's like, okay, you think they're the same, but or and have 2 very completely different meanings in the world of mathematics. Okay, in the world of mathematics, or and are totally separate things that have their own rule sets associated with them. So we need to be aware about that and make those necessary adjustments when we see those types of problems. Okay. Okay. So hopefully that went over well. Yeah, it's a little tricky. Throw those trick questions in there because, I'm mean. Yeah. I'm mean, and mean things is what I do. All right. I am Natty. That's absolutely 1,000% true. I am the meanest dude ever. All right. How would I calculate the probability of rolling a 3, then a 5? Ah, that would be done in, well, we're going to do that in section 5.3. But that would actually be, you would have to understand one thing here, is that there are 2 separate events if you roll 2 separate rolls, because the roll from before doesn't affect the roll that you have after you roll a 5. So you roll a 3 first, and then you have a separate independent roll, you roll a 5 on the second throw. So you have a 1 out of 6 chance on the first one, and you have a 1 out of 6 chance on the second one. So it'd be 1 out of 36 actually. You'd actually multiply in that case as opposed to addition. So 1 out of 36 chance of rolling a 3 and then a 5. So we'll actually look at that in section 5.3 there. But yeah, they're two separate events when you roll two separate times. So they don't have anything to do with each other. But it is a fair question, absolutely. All right, let's take a good look here at another problem. Yeah. All right. This time here, let's look at 35. Yeah, so let's look at 35 here. Okay. So 35 says a college survey. So in a national survey conducted by the Centers for Disease Control, determined college students' health risk behaviors. College students were asked, how often do you wear a seatbelt when riding in a car driven by someone else? So a bunch of people have answered here. Some people say never. Some people say rarely. Some people say always. You get the general idea. By the way, you should wear your seatbelt. It's kind of a thing. Um. Uh. Anyway. Um. So letter A, construct a probability model for seatbelt use by a passenger. All right. So construct a probability model for seatbelt use by a passenger. Okay, so you can figure out the probabilities by taking all these the relative frequency. That's all it's asking here. But let's take a look here at a couple of these. All right. I want to look at letter B here specifically. Would you consider it unusual to find a college student who never wears a seatbelt when riding in a car driven by someone else? Okay, so what this is asking us to do is we have to use the metric of unusual here. Okay, and to determine how we can use that as a comparison, we need to find the probability of never wearing a seatbelt because, you know, you do things that aren't that smart by not wearing a seatbelt. So they say never. All right, now the question is, how do we find the probability of never here? What should we do here in this case? How can we find the probability of never? What do you think we could do here based on this table you see here for 35? Okay, we have to divide. I agree with that, Natty. Question is, what numbers are we going to divide here? What questions are we going to divide here? That's a very good, yes, I agree. We have to divide by the sum of the frequencies. Okay, so this is going to be the sum of the frequencies. Agreed. All right. What should go on the top then? Frequency of never. Okay, good. That's right. Nice. All right, so 125 over 4775, okay? So if we add up the frequencies there, then that's what we get. Wait, 4775? Check that one more time. Pretty sure that needs to be a 6, right? So 4776? Yeah, okay, it is 4770. All right. I was thinking about that for a second. I'm like, should end at a 6. So, all right. Good stuff. Okay, and let's go ahead and see what we get here. What do we get as a decimal? This time we do want a decimal here. What's our decimal here? 125 divided by 4776. Let's do that on a calculator. What's that going to be? Okay, so point 0262. So just be a little careful there, Mazdy. You have to be a little bit careful there. Oops. I gotta be careful about how I write that too. So point 0262. Okay, so point 0262 there. Yeah, just make sure you have that rounding down. 4 decimal places there. Perfect. Now, would this be unusual? Yes or no? Is this unusual here? Yes. Right? This would be unusual. So yes, this would be unusual here. I remember in the 1980s, you wouldn't, if you were a kid, you never wore seatbelts in the back seat. So that was like the standard rule there back in the day. You didn't wear seatbelts in the back seat back in the 80s. Then again, our car here, or my car back when my first car that I remember our family having, at least from my perspective in the 80s, was a 1976 Monte Carlo. Maybe you guys have seen that car before. A 1976 Monte Carlo had seats that were kind of like this. They had the full-on seat there. So yeah, my mom was the regular driver of that car, but they had the full-on seat like this for the Chevy Monte Carlo. So yeah, I would sit in the middle or I would sit on the side, and then I think I'd put a seatbelt on in the front, but I would never put a seatbelt on in the back. Me and my sister. So like this thing is like a super tank. Like there's no question about it. My mom crashed the Monte Carlo eventually in the 90s. She crashed it in front of the library of all places. But like I remember she got into a wreck with like this smaller like Dodge Neon type of car. And the bodies of those cars are super cheap. So basically that thing crumpled like it was paper. And the Monte Carlo took damage because it's made of steel. So it was too expensive to repair, so we had to scrap it. But um, yeah, it was like the thing is built like a tank, like way back when. They like seriously just built like a tank. Thing that had a terrible gas mileage though, absolutely abysmal gas mileage. It was probably one of those cars you take on short trips, and then you never took them on long trips. I think the craziest thing my mom did with the Monte Carlo though is she my mom told me the story here. She chased some bank robbers actually using the Monte Carlo while I was sitting in the back seat when I was younger. So, yeah. Um All right, so here's what happened. We were living in Decatur, right? And there was a there was a robbery, right, at a Kroger. These couple guys come in. There's a robbery at a Kroger. I guess I was there with her, and she was like, I need to, she's like, I gotta go chase after him for some reason. So we're in the Kroger, and she like books it out of the Kroger with me in tow, throws me in the back seat, and she's like booking it like 60, 70 miles an hour down the highway trying to chase down these crooks because they took some money. And she's just like, I still don't even know why to this day. She went ahead, she decided to chase these robbers. They eventually got away, but I haven't looked back and like, why? Why did you even do this? I mean, you could just let it go. It's like you just need to let it go. It's like it's over. At least you're safe. It's like, no, I had to go get him. It was just like this manic need to go get him and go chase after him and let the police know like they have to go after them. So like ready to ram him with the car. I'm like, oh my gosh, like I'm sitting in the back seat. What's going on here? So, uh, yeah, it's so random. I ain't gonna lie. All right, good stuff. Let that be a lesson to everybody. That's exactly why you should wear your seatbelt. Don't follow what we did in the 80s. Don't do it. It is not nice. Not nice what happens to you in the car when you're not wearing your seatbelt. Too many of those. All right. Okay, any questions about section 5.1 before we move forward? I'm going to move forward here. Just a second. Any questions so far? Again, type no in the chat if there are no questions. If there are, please type those out as well. Not yet with a double T. All right. Yeah, I can do that. Here you go, Grant. Noper or nope? I don't know which one you want to say, Susan, but both of them are probably okay to convey what you're trying to say. All right, very good. Don't worry, you could go with this word here. Okay, let's just go with that word, and then you'll be fine. All right. You're fine, Susan. That's a real word. That's a word to go with. Yeah, pneumono ultramicroscopic silico volcanoconiosis is very simple. Very simple to say. Very simple to say. Of course I googled it. I'm too lazy to actually spell it. Of course I am. Copy and paste, that's the way to be. Although I remember my sister asking me to spell that once, and I did. By some miracle. Okay, so we are about 50 minutes in here, ladies and gentlemen. We're going to take a short break here. All right, so we're going to go on from question 6 here and move forward here with the rest of the next section here, talking about equally likely outcomes and whatnot. Okay, we'll talk about some methods here as well. So we're going to do a little bit less rest of the section 5.1 here, which isn't a whole lot, and then because we already kind of talked about it, and then we're going to do section 5.2. So that is what's on the agenda here. Let's take 10 minutes here. We'll come back at 7:05. Okay, so 7:05. 7:05 return here. That's here in 12 minutes. Okay, so 7:05 return. All right. So let's go ahead and do that here. And we're well on our way to doing a very good thing. Okay, let's do it. Yeah, go for it, Natty. What's going on about the practice test? Or the practice test is exactly like the real test, just different numbers. Yeah, I remember that. What about it? I remember we just had to do sample standard deviation. That's all it wanted. So sample standard deviation, sample variance. That's all it really wanted at the end of the day. Oh, okay. Yeah, so if you read the question there carefully, it was just about, it just wanted sample variance and sample standard deviation, that you can use the calculator to find sample standard deviation, and then you just square that, and you can find the sample variance directly from that. So remember, using the 1 var stats function on the calculator. Yeah, so there's 2 types, right? There's sample and then there's population standard deviation. So you want sample standard deviation for that. Yes, that's right. So Sx is the sample standard deviation. All you have to do is square that number to get the sample variance. I know it asks it out of order, but that's pretty much how you get that. Cool. Yeah, square the entire decimal number that you get for Sx. Correct, right. Yeah, go all the way out and then square that number, and then that's going to be your variance. So that'll be your first part of your answer, and then part B will be, hey, just put the sample standard deviation, which then you round to whatever they want. Yeah, that's cool. No problem. Here to help. You're halfway there. Very good. Does the practice test tell you the answers after you finish? Yes. It will give you proper feedback about what problems were wrong and what problems were correct after you finish. So it's it's exactly like a test. It's just gonna give you that feedback. And again, the practice test is exactly like the test, just with different numbers. So you'll have a good idea about what methods to use in every question on the test. All right. Yes. Histogram frequencies, yes. We did talk about histograms and frequencies. This is true. I'm just curious what your question was there, Natty. So that's basically going to be your relative frequency, right? If it talks about that. So if your histogram talks about a relative frequency chart, then you can find out via that way, because your relative frequency will be like your percentage. Or if you have a frequency distribution, figure out what your frequency is, add up the frequencies together, and then take the amount of that category, right, that 120 category, take that and divide it by the sum of the frequencies, much like we just did here in our example we just did here for probability, and that'll get you the same answer here. So you just take everything above 120 there. Unless it's the 68, 95, 99.7 rule. Jade, how you doing? How we doing? You guys done with Valheim tonight? It's pretty late over there. I ain't gonna lie. It's 1 o'clock in the morning over there. How are James and Milky doing? I hope they're doing okay. Right on. Sorry, I've been busy all day today. I apologize. Apologies, I really haven't. I've been so busy today, so just kind of moving around all over the place. Ooh. Ugh. No more incidents at work, I hope, Jade. That's good. There. Hey, nobody likes creepy people, okay? We protect our circle. Okay, that's important. That's how it works. Creepy McCreeperson has to come around. There's a lot of slapping that needs to be done. That's how it rolls. We could build him a house in Valheim, Jade. We could build Raymond a house. And we just call it the House of Creepers. We'll trap like a bunch of graylings in there. Legit. Alright. Let's do this. Alright. Alright, ladies and gentlemen, we're gonna come back here. Let's start off with the second half of class. Let's do this. Alright. Let's go back to our main screen here. Okay. Alrighty. Oh. Be helpful if I don't do that. Okay. We are back, ladies and gentlemen. We are back. Alright, so today in this second half of class, we are going to do the latter half of section 5.1. We'll do 5.2 here, which pretty much seamlessly goes with these last few bits of questions. So let's go ahead and talk about it right now. All right, so number 6, how do we compute probabilities of equally likely outcomes? Okay, so we've already talked about this here, but again, let's just do this for formal sake. It says if an experiment has n equally likely outcomes, and if the number of ways that an event A can occur is m, then the probability of A, that event A, P of A, is equal to the number of ways A can occur divided by the total number of possible outcomes. So we looked at that there in the last problem. We said, okay, well, how many people are wearing seatbelt? Said, I'd never wear a seatbelt. We said 124 said it out of the 4476 or 4776. And then we figured out the probability based off of that. Okay, so that, this is okay. This is the number of possible ways, that number of people who said no to never wearing a seatbelt divided by, say, the sum of the frequencies, total number of possible outcomes, which again is going to be the total number of people, like in that instance. Or again, rolling a 2 or a 3, for example, that's 2 possible outcomes. Possible outcomes is 6, okay? Something to that effect. Okay. As we've pointed out earlier, we have to watch out for the wording here of the event in question. That is something that is very important here that we will need to keep in mind. Okay, so you definitely have that there. All right, so we've kind of looked at that already. So I'm going to move on from this and we'll move forward. Okay, so let's go ahead and take a look here at number 7. Okay, so number 7 says, what is the empirical method? All right, what is the empirical method? All right, so the empirical method is a probability experiment that usually involves a large amount of trials of an experiment. Okay, let's talk about this in a little bit more detail. All right, so a little bit more detail. Basically, it's like if we flip a coin. Now, if we flip a coin and we get heads or tails, okay, if we get heads or tails, then basically there's a 50-50 chance we're going to get heads or the 50-50 chance we're going to get tails, okay? That's what we think, okay? There's 1 out of 2 chance that one of those two is going to be true, all right? That has to happen, all right? Now, if you flip a coin 10 times, for example, then maybe 7 out of those 10 times a heads appears, for example. But the expectation is it should be 50-50. Now, it's just like 7 out of 10 times, so there's a 70% chance that heads shows up. Well, the answer is 10 flips of a coin doesn't exactly tell you an accurate representation of the odds of heads or tails appearing on a flip of a coin. 10 people in a survey doesn't tell you a whole lot or anything, all right? If you have millions and millions of people here. I'm sorry, what? Note about the class that needs to stop for I oh, Sorry, you weren't supposed to see that. I'm terribly sorry about that. Yeah, biological hazards stay on the other side of the screen there. Yeah. Yeah. Virtual. Yes. All right. Just for funsies. Okay, so flipping a coin 10 times doesn't tell you exactly the amount of odds that an actual coin flip is going to take. We need to be as close to 50-50 as possible. So maybe you don't flip the coin 10 times. Again, surveying 10 people doesn't tell you anything. You need to survey much more than 10 people. Maybe 500 people, 1,000 people makes a whole lot more sense. If for a coin, for example, you may need to flip the coin 10,000 times. All right, you may need to flip a coin 10,000 times to ensure that you will indeed get a 50-50 split. Okay, so you may flip the coin 50 times, but that's not going to be enough. You need to flip the coin 10,000 times, all right, to see, does it actually come up to be a 50-50 split? And eventually, if you do that many, many times, you actually will show a more of a 50-50 split over time. So if you see a lot of times, why is this empirical method very important? Well, a lot of modeling does like not just 10 trials, it may do millions of trials. So millions of simulations, for example. Or if you're talking clinical trials, I need 10,000 people to take a clinical trial so I can get proper, more reflective data than say 10 people. Okay, things like that, they definitely matter. Okay, so we definitely have that. Now, so that's the empirical method there. All right, let's move on to the next question here. What is a compound event? And we're going to talk about compound events here in this next section. So a compound event here are basically two or more events that can occur. Okay, so we have two events, A and B. Okay, E and F is what they call it in the book, but I call it A and B. And we define whatever A and B is, and they occur, right? So again, rolling a 5 or rolling a 6, okay, compound events that can occur. Now, one thing that we do need to look at is with those two events that can occur, like rolling a 5 or rolling a 6, or whatever the case may be, let's take a look here at two very important things here. So we're going to look at the next question here, which says, what does mutually exclusive / disjoint mean? Now, this is something that you probably have seen before, just maybe not in this manner with probabilities. So basically, this is the formal definition here: two or more events that have no outcomes in common. So there's literally nothing in common between A and B. So when we say mutually exclusive or disjoint, meaning they're totally separate things. Okay, A is over here and B is over here. Okay, two separate things, two separate guys. They have nothing to do with each other. So if I look at it from a pictorial perspective here, just a simple picture perspective here, I would have, say, this is my sample space here in this box. Let's say this is my sample space. And I have my event A that has some amount of outcomes in here, and my event B that has some amount of outcomes in here. So if you've seen a Venn diagram or whatnot, then this should look fairly familiar to you. Maybe you did this in bio class as well, so that probably makes sense as well. All right. So, and again, these are two separate things. They have nothing in common with each other. Now, there is a result that goes along with this, so get that result here first. Okay, so if they're mutually exclusive, then okay, so we got to be careful about this part here. All right, so please be very careful writing this in your notes. All right, so if they're mutually exclusive, so if A and B have nothing to do with each other, then the probability of A or B, probability of A or B is equal to the probability of A plus the probability of B. The probability of A or B, probability of A plus the probability of B. Okay. However, we can have a situation where A and B do have something in common. So let's change this up a little bit. Let's change this to having something in common. So what if they're not mutually exclusive? Well, we have this situation here where you guys have seen this before, probably in maybe in some form or fashion. All right, but here, again, they share something in common here. All right, so this middle portion here, they share something in common, like A and B. All right. Now, here's the question. What do we do for A or B? So let's take a look at what happens when we have a not mutually exclusive event. In this case here, the probability of A or B is equal to the probability of A, the black circle here, plus the probability of B, which is the red circle here, minus the probability of A and B, which is this middle part right here. So this middle part right here, I think maybe here if I put a bucket in there. All right. So here we have, again, we got A, we got B, and then this blue part here is going to be where they both overlap. We're going to take away one of these countings here. Now, why does this happen? The reason why this happens is because we count A, so we count this whole black circle here. We count B, we count this whole red circle here, just like we did if they were separated. The problem is that we counted this middle portion, which is A and B, 2 times. So what we need to do is, and as the note says here, we take away double counting. Since we double counted the middle part 2 times, we then remove one of those double countings, and then we get our proper probability here after we take away that proper double counting. Okay, so want to do that here in these cases if there is something indeed in common between A and B. So now let's take a good look here at some problems. All right, let's look at some examples and let's apply them right away. Okay. You have school in 7 hours. Oh man. I know it's tough. I know it's 1 o'clock in the morning over there in the UK. But you gotta hang in there, buddy. Gotta get some rest so you can get online or go to school. It's important. Degrees make the monies. Go with that. Degrees, monies. It's important. I assure you, you'll do well, though. Put in the time and effort, you will do well. Let's see. What do I want to do here? What am I doing? Is the thing. I think it's 262 here. Oh, start. All right. Forward. All right. Okay. So let's take a good look here at number 29. Okay, we're going to talk about, we're going to look at number 29 and do some examples from that. All right, so let's do it. Okay, let's look at 29. All right, so 29 says is Medicare fines. So let's do this here. So, in an effort to reduce the number of hospital-acquired conditions such as infections resulting from the hospital stay, Medicare officials score hospitals on a 10-point scale with a lower score representing better patient track record. The federal government plans to reduce Medicare payments to those hospitals with the worst scores. The following data represents the scores received by Illinois hospitals. All right, so here's the frequency, how many hospitals are in the score ranges. That's great. Okay. Now, having said that here, let's look at what we have here. All right, so let's answer some probabilities that go along with this. So What's the probability? Let's start off with something easy. What's the probability that we have something between 5 and 5.9? So what's the probability that we have something between 5 and 5.9, according to our table that we see here? What do you guys think? Probability between 5 and 5.9. All right. And how do we get that answer there? Okay. Okay. 23 out of 125. Okay, good. That's right. Yep. I agree with that. And so you would agree, again, 0.184, as was correctly stated from before by Ujwal and Mazdi. Okay, good. Perfect. All right. Excellent. That is correct. All right, so no problems there. Easy peasy. Let's try another one here. All right. Let's do this one here. It's the probability. What's the probability that it's not between 5 to 5.9? So let's take a look at that here. The probability of not between 5 and 5.9. What's that going to be? Not between 5 and 5.9. What can we do there? Okay. Now, I'm going to highlight something here. This is kind of a trick question on purpose. 102? Okay, actually up. I'll go with that. Why not? This is kind of a trick question, but I'm going to run with this. 102 out of 125. That part is correct. Yes. That's actually correct. Yes. There are 23 in 5 to 5.9. That means everything else has to be outside of 5 to 5.9, so that would be 102. And if we divide this, I don't know, what do we get here? Oh, I know what I get. Okay. I'm going to take a wild stab at this. I'm going to say that's 0.816. Did I get that? Did I get that right there? 0.816. All right. Good stuff. Now the question is like, whoa, 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 wait a second here. Timeout, timeout, timeout. All right. Now maybe you went ahead and you added up all the values that were not between 5 and 5.9. And that's fair. Okay, that's exactly how you could do that, right? Without a problem in the world. All right? And that part is absolutely right. But maybe there's a different way of doing this. Okay? Maybe there's a different way of approaching this type of problem. Okay. So what we're going to need here is we're going to need another tool to help ourselves out. So the other tool to help ourselves out is this last question here on this handout. What we also employ is if we're looking at harder problems here, which we will in this chapter for sure, especially the next section, we want to use what's called the rule of complements. So what does complement mean and the rule of complements? So first of all, complement isn't something nice. Instead, complement in mathematics means basically not that. Okay, that's correct, Ujwal. That's right. So our notation here for complement is a complement, so some event, and put a c there as an exponent. And as Ujwal has correctly pointed out here, if we want to find the complement of something, the probability of not that event happening, is equal to 1 minus the probability of that event happening. So if we're given the fact that we're not between 5 and 5.9, then the probability of not to 5 and 5.9 is exactly stated as what Ujwala's has, 1 minus the probability of 5 to 5.9. So now I don't need to worry about adding up all the numbers between 1 and, from 125 and all that stuff. I don't need to worry about that. All I need to know is I can take away the first 23 and I'll be left with the 102, or I can use the previous, you know, answer, and I can do 1 minus 0.184 because I know that's the probability of 5 to 5.9. And here I get 0.816 as our final result. Okay? So we have that there. There you are. Okay? Okay. Any questions about that so far? This is something that we're going to use and use quite a bit for harder questions, especially. Again, sometimes it'll come down to wording there, so we just have to be a little bit extra careful about where we use this, but it sometimes makes things actually significantly easier by using the rule of complement. All right, Susan has no questions, okay? No. Oh, posture check, of course. Let's set up a bit straighter. Thank you. Alrighty. All right. No questions? All right. Let's go ahead and do another one here. This time we're going to take a look at a table here, and let's see what we get. Okay. Oh, okay, so we're going to look at number 40 here. We have a contingency table that we talked about here back in chapter 4. And now we can work with contingency tables using that with probabilities. So let's take a look at 40 and let's see what we're working with. All right, so here we have some categories here. We have, let's read this off here though. A guidance counselor at a middle school collected the following information regarding the employment status of married couples within his school's boundaries. Okay, so here we have the number of children under 18, 0, 1, or 2 or more. And depending on who worked, if the husband worked, the wife worked, or both spouses worked. Just depends. Okay. Let's take a good look here at this and let's see what we got. All right, so let's look at, I'm going to skip letter A because letter A is just kind of a rehash. Um, let's look at, let me close. Oh, sometimes, okay, that one's not what I wanted. I'm going to go skip to letter C then. For some reason, I thought there was an R in there, but there was not. Okay, letter C. What is the probability that for a married couple selected at random, the couple has 2 or more children under the age of 18 and both spouses work? So, 2 plus and both. Okay, so what we're given here, we're given the amount of people here. We surveyed 1,700 people here. So how many people have 2 plus children and both work? How many would that be? Okay, 2 plus and both work. So 2 plus and both work. $370. Okay, good. That's right. So 370, let's take a look at the chart here. Okay. So we want to find out how many of these people where both of them work and they have 2 plus kids. So we see 2 plus kids break down like so, and both spouses. So again, whereas both spouses and 2 or more, 370 out of 1,700 people that were surveyed fall underneath those two categories simultaneously. Now all we need to do is figure out what the decimal equivalent is of 370 over 1,700. So can anybody give me an answer for that? 0.2176. Okay, good. All right, very nice. That's right. Excellent. Okay, let's look at letter D. Okay, so we have that. That's fine. Take a look at the next one here. It's probability for a married couple selected random. The couple has no kids, or only the husband works. So 0 or the husband. Okay. Now, you got to be careful about this here. Remember, wording is very important, as I've pointed out here already. So if wording here is very important, it says 0 or husband. Okay. Now, according to this contingency table here, there may be something in common between 0 and the husband. Okay. Let's write out our little formula here. Okay. So we're using our general addition rule that we have here. Here for a second. Remember, we're going to go ahead and use this one here because maybe they have some number in common. We have the probability of 0 plus the probability of the husband minus probability of 0 and the husband. Okay. Okay. All right. So let's take a good look here at each one. How many people are in the 0 category? How many people have zero kids according to our survey? 788. That's right. We have 788 people have no kids. It's fair. All right. How many people have a husband that only works? Take a look at that. We have to add the husband to the category here. What the husbando? Husbando. 425. Okay. Now we want to subtract because we double counted because they do have something in common. How many people are we subtracting here? Take away the double counting. All right. So again, this is 0 and the husband, right? So Mazzy, that's correct. Okay. 172. So here we have 0 and the husband. So if you think about it this way, here's another way to visualize it. Again, we counted the people in the 0 category. So this 172 94, 522, we got the 788. We also counted the husband category, which had 425 people, and we counted this 172 a second time, along with the 79 and 174. So because we counted the 172 a second time, we're now subtracting that 172 here to remove the double counting that we just did. And we're going to divide that all by 1700, which is what we surveyed. Okay. All right. We should get here 1041 over 1700. Okay, 0.6124. All right, good. All right, nice. That is correct. Good. Very good. All right, any questions about that? Sure about that. Questions, questions, questions. Nope. So we picked 172 because the outcome of the husband only with 0 kids. Yes. That was what overlapped. So husband and 0 was 172. We had counted 172 twice after we counted the 0 kids category and the husband category. So if you just kind of trace your hand, you said, okay, I counted 172 the first time. Now I count 172 again if I'm going across. So I need to remove one of those 172 counters, and then I'm going to have my answer there. So there was a bit of overlap there with the 172. No problem. Here to help. Any other questions before we move forward? No. Okay. Gotcha. All right. Let's look at the last one here on this particular one. Nope. All right. Would it be unusual to select a married couple at random for which only the wife works? So unusual if the wife is the only one that works. So can anybody tell me here what's the probability that the wife only works? Probability that only the wife works. And is that unusual? So it's 126. Okay. So I agree with the 126 out of 1700. All right. And so we get, let's go ahead and do that there. 0.0741. Okay, both of you are correct. Okay. So is this unusual? No, it is not unusual, right? It's low. I mean, that part is true. Not unusual, right? It's very low, but it's not considered unusual based on the metric we use. So it has to be less than 5%, and it doesn't meet that threshold. It's over 5%, so it's not as unusual as people think it would be. Reason. All right. Very nice. Very nice. Very easy. Easy peasy, lemon squeezy. Winner, winner, chicken the diner. Okay. Any questions about section 5.2? Hopefully that wasn't too bad. Hopefully that was a little bit easier. So, okay. Okay, very good. So that's the end of section 5.2. That's what I have planned for you today. Next time, on Wednesday, we're going to move forward here with sections 5.3 and 5.4. That is what is on the docket here for the next class. So we're pretty deep into probability now, so we're going to have a little bit of fun, certainly looking at more examples here. But again, next time here, just going to give you a warning. Got to keep on your toes about that wording. We're going to see more of that wording here next time. That is going to be, excuse me, that is going to be pretty tricky to use at times. So we have to be a little bit more aware about the wording here. That way we don't get caught up. Today we just saw ands and ors, but now we're going to introduce another wording here. So again, we're going to keep on our toes here, make sure that we cover our bases in terms of the wording here in several of these problems. We can apply the correct procedure and probabilities associated with that. So that is what we have for our agenda. Isn't that nice? We're in good shape. We're in good shape, ladies and gentlemen. We are in good shape. We're on a good path to victory. All right. Again, as a friendly reminder here, remember the homework and tests are due. Okay, by Sunday at 11:59. All right, Sunday 11:59. All right, so be sure to finish that up before then. Otherwise, sadness will ensue. And and we obviously don't want sadness. I like happiness. I'm sure your grade likes happiness too. So, giving you plenty of time of which to finish that. No sadness, yes. Nadia, we're trying to avoid sadness. Yes, this is true. Avoid sadness. I agree with this. That's what I'm trying to have happen. Nobody's sad in the class. Everybody is trying their best and doing their best. Okay. Again, if you guys have questions, you guys feel free to email me. Okay, I'll be more than happy to answer your questions. Okay, or again, if you have a question for Wednesday, you can bring it on Wednesday. That's perfectly fine as well. All right, everybody. I hope everybody is okay. All right, so that'll take care of it for today, everybody. Thank you so very much for coming out here to the stream once again. All right, everyone, have yourself a very wonderful evening. Stay safe, stay healthy, and most importantly, everybody, stay sane. We will see you on Wednesday. All right, have a great one, everyone. Take care of yourselves. All right, bye.